afternoon, friends. Continuing with classical mechanics. In the morning, we have discussed the brief introduction of classical mechanics. I will continue with the same. As I mentioned in the morning, we have two techniques. One is Newtonian mechanics, the other one is alternate mechanics called as analytical mechanics. Here in Newtonian mechanics, a problem solved using Newtonian mechanics or using Newtonian approach needs the evaluation or needs to know all the forces present in the mechanical problem at all the time. If a mechanical problem is having constrained forces which are involved in the mechanical problem, those forces should be known at all the time. It should be evaluated, number one. The second is all these forces should be resolved, and then unimportant forces involved in the problem should be eliminated, and this becomes another difficulty of Newtonian approach. So to overcome this difficulty of Newtonian approach, Lagrange, D'Alembert, Hamiltonian proposed an alternate method known as analytical method, called it as analytical mechanics. In Lagrangian formulation generalized coordinate concept is used. Well, we'll discuss in detail what are generalized coordinates, how they are considered in a given problem in coming classes. In Lagrangian formulation, they consider generalized coordinates, namely the position and velocity. Fine. They consider it as generalized coordinates, and they form a second order linear differential equation. In another technique known as Hamiltonian technique, they consider position and momentum as generalized coordinates, and they get first order linear differential equation. By the time this scientists have developed an alternate method to Newtonian mechanics, this partial differentiation have evolved, and they have used this system of differentiation or partial differentiation to simplify analytically a mechanical problem. Well, let us go to another important article of your syllabus, constraints. Fine. Constraints often the motion of a body or a particle may be limited by some ways, may be restricted by some ways. So the restriction imposed on the motion of a particle or on the motion of system of particle known as constraints. In a simple words, we can say that constraints are called as condition imposed on the motion of a particle, motion of particles or a system of particles is known as constraints. Before I go for the detailed definition and the explanation, I want to give some illustrations, examples, through which you will come to know what is meant by constraints. But in very first example, say example of a rigid body. Fine. In physics, we consider rigid body is a body which is solid, a large body having large mass. The important concept of this rigid body, a model, you can say all the time distance between any two particles is always constant. In case of rigid body, distance between any two particles is always constant. Even the body is under force, even body is in motion under the influence of external as well as internal forces, the distance between any two particles is always constant. And this is the constraint, this is the condition we are imposing on motion of a rigid body. This is one example of constraints or constrained motion. Let me take another example here. Motion of a simple pendulum. We are familiar with this. Many times we discuss this in physics. In case of simple pendulum, mass of a point object or point mass is at a certain distance from a rigid support. This is point mass. This point mass is at a certain distance from the rigid support, and distance is L, and this is kept constant. That means motion of mass of simple pendulum or motion of the point mass in case of simple pendulum is restricted, it's limited. The constraint here in this example, the length between the rigid support and the point mass is constant. It is kept constant. L is equal to constant. And this is a constraint or a condition limitation we are imposing on a mechanical problem called as simplest problem of mechanics, that is simple pendulum. Here length is kept constant. Of course, there are examples where in case of simple pendulum length is varying with time. Here length remains constant. In this simple example, length is kept constant. Point mass is at a certain distance from this called as the rigid support. And this is the constraint we are imposing on a mechanical system here. Let me take another example. That is, say gas is filled in a container. So third example, gas is filled in a container, and see the container is closed. I want to say here, this is a container and the gas molecules are filled in it. Let us see, these are the dots represent gas molecules here. There are innumerable gas molecules, we cannot count them. And say the gas is enclosed. Now, we have known as per the kinetic theory of gases, molecules of the gas, they are in a random motion. So the motion of the gas molecule within a container is restricted. Motion of all the molecules is restricted within the wall of the container. That means molecules are allowed to move here and there in all possible directions well within the container only. That means the molecules having restricted motion. The constraint imposed on the molecules, they can move well within or well inside the container. Motion of the gas molecule is restricted, and this is another example of constraints or a constrained motion. When we impose a constraint, a condition, a restriction, a geometrical restriction on the motion of a body, the motion of a body is known as a constrained motion. In case of simple pendulum, we apply the condition, that is the length of the simple pendulum is a constant. Point mass is at a constant distance from the rigid support. The constraint is its length. We restrict the motion of point mass of the simple pendulum, keeping the length constant, and that is constraint. And the motion of the simple pendulum is known as constrained motion. Even in case of rigid body, say the distance between any two particles is always constant under the influence of external as well as internal forces. The constraint is the distance between the two particles. Any two particle is always constant, and that is the constraint here. If such a rigid body is in motion, we call it as constrained motion. But let us take another example. Say example number 4. Well, a particle or a system of particles is allowed to move on the free space. The particle can move in any direction. Say in a Cartesian coordinate system, particle can move along x direction, particle can move along y direction, particle can move along z direction. That's free space particle. When we keep the particle on the surface of the sphere, so this is part of the sphere. When we are keeping the particle on the surface of the sphere, particle is allowed to move only on the surface of the sphere. That means its motion is constrained motion. And the constraint here in this case, particle is allowed to move only on the surface of the sphere. That is a constraint. Looking at these examples, we can say that constraint is a condition, a geometrical restriction imposed on the system of particles or on the particles to have constrained motion. Well, in constrained motion, particle cannot move arbitrarily. It cannot move arbitrarily. So the constrained motion is a motion which cannot proceed in any manner, cannot move in any direction. It should follow a specified motion only. It's known as constrained motion. Well, this constraint motion can be classified into two types. Constraints are further classified into two types. Constraints are classified into two types. So constraints, we have two types. I'll write here what is called as holonomic constraint. And here we have non-holonomic constraint. We'll discuss one by one because this happens to be in our syllabus and we are discussing constraints. Well, what is the use of constraint or constraint motion? Why we are studying this? Why people have studied this? Well, constraints. Knowing the constraint in a given mechanical problem and eliminating them. Once you know the constraint in a given mechanical problem, once you identify the constraint in the system or system of particles, you can eliminate them. By eliminating them, you are reducing the number of coordinates. That means constraint reduces the mathematical description of a mechanical problem. So, when we have started solving a problem, we will solve it in near future. Definitely we will solve the problems. Lot of interesting problems we can solve on this. Say there is system of particles. There are n number of particles, and there are certain constraints imposed on a system of particles. When we say constraints imposed on a system of particles, we identify them. Let us identify the constraint. Let us try to know the constraint and then eliminate them from your problem. Once you eliminate them from your problem of mechanics, you are simplifying the description, what is known as mathematical description of your problem. And once again, we'll have the examples based on holonomic or non-holonomic constraint. Looking back, coming back to this, constraints are classified into two types. Well, holonomic constraint and say a non-holonomic constraint. Well, holonomic constraints, here holo means in Greek language, this is integer, and holo means whole in Latin, or integrable. We know the integration. Integer, holo means integer in one Greek language. Whole, W-H-O-L-E, whole in Latin means integrable. So holonomic constraints are the constraints which can be expressed in the form of equation. Holonomic constraints are the constraints which can be expressed in the form of an equation. Well, equation relates the relation between constraint and the coordinates. For example, say f of I, x1, y1, z1, x2, y2, z2, so on up to xn, yn, zn and t. Well, I gives the number of constraints. F of I is some function of coordinates here. x1, y1, z1, x2, y2, z2, xn, yn, zn are the coordinates of a system of particles, which here we have written the equation for a system of particles having n number of particles. And this is the equation for higher constraint here, that is written equal to I gives the number of constraint here, x1, y1, z1 or x2, y2, z2, xn, yn, zn are the coordinates. This is the relation between constraint and the coordinates, which is equated to 0. So any constraint which we can express in the form of equation, is known as holonomic constraint. Well, we'll have the examples here. Later on, we'll discuss this non-holonomic constraint. Let's go to the examples of holonomic constraint. So, examples of holonomic constraints. I'll give here one example. That is example of simple pendulum. Say examples of holonomic constraint. Well, I have here a rigid support, and this is the, say, my x-axis. I write this as, say, x-axis, and say this is y-axis. This is origin, I write it as O, and I have here a pendulum. I want to know the position of point mass of the pendulum. This I write it as P, stands for position P of xy. So here the pendulum is allowed to move in a xy plane. Consider the simple pendulum case in which the pendulum is allowed to move in an xy plane. This is theta, and we write this as L. So here, to describe the position, the constraint, basically the constraint is this. What is the constraint here? The length of the pendulum is kept constant, or point mass of the pendulum is at a constant distance from rigid support. L is constant. Now, I want to write the equation for the position. I want to locate the position, or I want to find the position of the simple pendulum at a given instant of time t. To locate the position, I need two coordinates. Because it is moving in a xy plane, I will take x as one coordinate, y as one coordinate. I can write it is equal to x square plus y square is equal to L. If I write this as equal to x square plus y square is equal to L square, not L, then we can, instead of using this two coordinates x and y, I can use only this, that is polar coordinate. X square plus y square is, we can write this equal to position coordinate r, that is r square is equal to L square, or r is equal to L. This is an equation. What I want to say here, we have discussed this example earlier also. I am repeating this example, and I am calling this as a holonomic constraint. Constraint which can be expressed in the form of an equation. If the coordinates varies with time, then the time concept will come in picture. Here the coordinates doesn't vary with time because the length is constant. So x, according to distance formula, we write it as x square plus y square is equal to L square. And if I take L and theta, or r and theta are the polar coordinates, I will reduce this equation into much simpler equation. Look at this. To find out the position of a point mass of a simple pendulum which is in motion in an xy plane. This is fixed at rigid support. Theta is the angle made by the string or the length. This is point mass which it changes, it's oscillating, we know that. P of xy is its position at a given instant of time which makes an angle theta. I want to express this constraint. Constraint is this L is equal to constant. I want to write the equation for constraint. To write the equation, I want to locate the position and at a given instant of time, the position of the pendulum or mass or called as point mass is x square plus y square is equal to L square. Or you can write R is equal to L using polar coordinates. We are using two coordinate system here, a Cartesian coordinate or a polar coordinate. Look at this. This is a Cartesian coordinate where we need to write the equation of constraint. We need two coordinates. If I select the proper coordinate system, I need only one coordinate, either theta or r. So I want to stress here the constraint motion reduces the mathematical description of a given problem. That means using this analytical treatment called as Lagrangian formulation or analytical mechanics, we are describing the mechanical problem and then we are simplifying by knowing the constraints. We are making it simple. We reduces the coordinates. That means constraints help us in reducing or eliminating the number of coordinates. That makes easier to us mathematically. A complicated problem can be made simple by reducing the constraints. This is one example. We can go for the another example, that is rigid body. I have mentioned rigid body. The constraint imposed on a motion of a rigid body is holonomic constraint. Reason for this: motion of a rigid body and the constraint imposed on it. What are the constraints here? Constraint is the distance between any two particles is always constant. So we can